stuff. Um, okay, here we begin. Today what we're going to look at is variable velocity from Unit 2. That's problem E1 with like the horse problem. And we're going to look at some graphical motion things that a lot of people are kind of struggling with in class. We're going to start with the E1 problem. This is the variable velocity. I've got my trusty calculator. Like I always say, it's got a pink back to it because that's what I got my junior year of high school. But a gray front. It's cool. Okay. In this problem, what we are trying to do is we are trying to find an average velocity. And an average velocity, if we remember from the labs we did, we kind of prefaced in the week 4 video, technically a change in a displacement divided by some change in time is an average velocity. But the key thing that we've done in the past, this has always just been the displacement is done at a constant velocity. So like you're always moving at the same rate. And the thing about this problem that's different is technically what an average velocity is it is a sum of displacements over some total amount of time. So if you're, thinking about walking down the street and then all of a sudden you break into a lovely skip, then you start sprinting, you've just changed your velocity because you're moving at different rates. And you've covered different displacements in some different amounts of time. So technically speaking, an average velocity is a sum, and this is a sigma here. It stands for a summation, and if you remember, summation means to add many of the same terms. So it's a summation, and we're going to sum up a bunch of displacements that we have here. And we're going to divide that by, ooh, that's a terrible sum, the sum of our times. So like how long we spent in each form of motion, walking, skipping, running. And basically this just boils down to I need a first displacement plus a second displacement plus a third displacement plus etc. until you get out to however many displacements you had divided by, and then the corresponding time for each of these displacements. So how long were you skipping? How long were you running? How long were you just walking around? Okay, and each of these displacements is in a time is linked together. Okay, and they're linked together through their own little equation, which is this original one. The velocity is equal to some displacement divided by time. So through this little equation here, if we're missing something, we can go and find it if we have two other variables. So if I have a velocity and a displacement, I can rearrange this and find time. If I have a velocity and a time, I can rearrange it and find displacement. If I have displacement and time, well, I really don't need to go find velocity because I have everything I'd like in the problem itself. So that's what we're going to use here in order to look for this average velocity, which is what we're digging to try to find. If we take a look at some example here, let's just pretend that we have a sneaking cat. I'm allergic to cats, and I swear there's like one secretly living in my house. I can't sense it, but I'm sneezing all the time. So this is our sneaking cat. Okay, let's pretend that this sneaking cat, if you've ever seen a cat kind of like sleuth around and whatnot, let's pretend it's like creeping forward real sneaky beaky like for a time of, I don't know, like 20 seconds. And then let's say while it's moving forward sneaky beaky like, it's moving pretty slow, right? Because it's like stalking its prey. So let's say it's moving at half a meter per second. Not very fast at all. All of a sudden, it sees something it likes, it wants to attack my face, whatever it is, and then it busts out into like a dead cat sprint, whatever that would be. So it's moving at like 8 meters per second, but it's only doing this for 3. That's the worst 3 I've ever drawn. It's only doing that for 3 seconds because it's like boom, 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 attack the face. Okay, so it's happening very quick. That's our second time here. So if we look at this, in both cases, the thing that we're missing is we don't know how far the cat has traveled. And here as well, we don't know how far the cat has traveled. And if we look back to our equation up here, well, if we have 2 of the variables, such as a velocity and a time, we can go find the third one, delta x, the displacement, which is what we're missing. If I would have changed this problem up, if I would have given you a displacement and a velocity, like I will on the boss battle, then you can rearrange this equation and find delta x. And just so you have all those equations, if you've got trouble working out the math or the algebra, the equation we have here is velocity equals a displacement divided by time. I can move the time over just like that by multiplying by t on each side. So I have a velocity multiplied by a time equals some displacement. And last but not least, if I then divided this velocity underneath, I can see that time equals a displacement divided by a velocity. So these are the 3 equations that we could be using right now. We'll get a bunch more in the coming weeks. But for right now, these are our constant velocity type equations we have here for non-acceleration. Because we're still not dealing with acceleration in the problem. We're assuming that the cat just bolts into that real quick. Okay? We'll see later on how the cat can like speed up as it's sleuthing around. Okay? So what we need to do is, if we're looking for the average velocity of this cat, that's what we're trying to find, then we need, because we have 2 setups here, if we're looking at the sum of all the displacements divided by the sum of all of the times, well, I need to find these displacements first, okay? I'm trying to set this up as the first displacement plus the second displacement divided by the first time plus the second time. And when I do this, these are in parentheses technically. We want to add the numerator and then add the denominator, then divide those quantities. But I need to find x1 and x2. I have t1 and t2. That's good. I need x1 and x2. So we can simply do this, solving for x1, looking at our equation right up here. If we want to solve for delta x, we've got this equation that's going to come in play, that delta x equals velocity times time. So I can simply say, okay, if delta x1, because I'm looking for this first scenario here, equals velocity 1 times time 1, then that's going to equal 0.5 meters per second times 20 seconds. Our seconds cancel out. That's lovely. We get meters, which is indeed a displacement. Half of 20 is 10 meters. I'll just shove that up there for completeness. If I do see the same thing for delta x2, or the second displacement, I'm going to link it to the second velocity and the second time. That second velocity is 8 meters per second. The second time is 3 seconds. Once again, those cancel out. I get 24 meters. Cool. I can plug 10 in there. I can plug 24 in there. I can plug 20 seconds there. I can plug 3 seconds there. So this will equal 10 plus 24, all in meters, divided by 20 plus 3 seconds. 34 meters divided by 23 seconds equals Before I pull out my trusty pink calculator, what would be most helpful for me to think about this a little bit? If I ignore the 4 and the 3, like I just kind of like, okay, what kind of number am I looking at here? If I ignore this 4 and the 3, I'm looking at about 3 over 2, which is about 1.5. And I can do that because these are each to the tens place. So if I do crunch into my calculator, 34 divided by 23, I get 1.47. So 1.47 is pretty close to 1.5. I like that. Units are meters per second. Woo! And that's how we do that type of problem there. It's just a matter of recognizing what we have, what we don't have. Okay? As a little sidebar over here, if you were looking for time, remember time is equal to a displacement divided by a velocity. We can prove that because that's like meters over 1 all over meters per second. Remember, when you're dividing by a fraction, that's the same as multiplying by its reciprocal. So meters over 1 times seconds per meter, they leave us seconds, which is indeed time. So whatever your velocity is measured in, meters per second, meters per hour, meters per minute, that time quantity is going to be what you're going to get in the end. Okay? So it is totally possible to solve for that. If I give you a displacement and a velocity, you can go get time just by following that equation there, and then you could just plug time back up wherever you needed it. Okay? In this case, we didn't have that, but if you ever see it, it's totally possible to do that. Okay? That was the E1 problem of Unit 2. Fin. Okay, any questions on this? For anybody sitting in chat. I know I got a few people in here.